Hey everybody, and welcome back to Linear Algebra Online. So the plan for today is to just do a few proofs related to like similarity and I guess more specifically like diagonalization. There we go. So a lot of these, just kind of as a quick refresher, if you have that like matrix, I'm just gonna use M and N. Matrix M is similar to N. Then you basically have that P inverse MP equals N, okay? Or all similar versions of that. So that's kind of like what we're basically going to kind of need to get in a lot of these problems. So in this one, it's just saying if B is invertible, then you should be able to show that AB is similar to BA, all right? And so to start off, I'm going to write a very silly but true statement. B times A is B times A, okay? And then if B is invertible, right, we know B inverse exists, right? And so that means that, so if we know B inverse exists, right, I can write down this statement, B inverse, right? A, B, B inverse. Okay, if you look at what that is, this part right here is going to cancel to an identity, right? So it's basically not there. It's just like I'm just writing something for purpose coming up. And then B inverse is B, right? So really this whole big messy thing is just BA, which is what I have there. And then what I'm going to do is I'm going to say let B inverse equal P. So B inverse is P inverse. And then if I use that, right, therefore I'm going to get basically P inverse, right, is my B inverse. And then I have an AB in there. And then B inverse is P, right? So AB, by definition, is similar to BA. And that does it. So it's just kind of a clever like use of B inverse to get the AB equal to BA similarity. Okay. So for this one, if you know that two matrices are similar, then actually their transposes are similar, which is nice. So I'm going to start in this one. We know A and B are similar, so I'm going to start with B equals P inverse AP, right? And I'm going to just start by taking the transpose of both sides. If I take the transpose, then there's not much to change over here. So I'm just going to do something on the right side here. Basically, I'm just going to use the socks and shoes transpose kind of property. We're going to have PT, AT, P inverse T, right? And then I'm going to use another property of transpose, which is that you can commute these two right here, right? You can swap those in now. So then I'm going to have PTAT, whoops, that's A, P, oh, that's horrible. PTAT, PT, transpose. There we go. That's a -1 wasn't good. I swear that's a -1. No, I didn't even do it. Oh man, I'm just not doing well here. Okay, there we go. So you probably see where this is going now. AT, BT, right, with matrices on the side. And so this is like the perfect setup for, just kind of redefining. We can do the same thing that we did above. I'm just going to say let P transpose equal like Q or something inverse, right? And therefore, we have that P transpose inverse, right, would be Q. And so if I go and swap in that stuff, then we have B transpose equals Q inverse, AT, and then Q, right? So A transpose is similar to B transpose. And that's it. So, if you were writing these up, you would probably obviously want to fill in some kind of filler words here, but these are definitely the idea of these kind of proofs. And I've got 3 more proofs I still want to do. And really any of these proofs today, I would recommend you pause the video and you try it yourself. This is usually the kind of harder types of problems that in linear algebra are these types of proofs. And so it's good if, you have this thing that you try it before I just jump into it. So, I'm going to jump into it now then. So this one says that if A is a diagonalizable matrix with only one eigenvalue lambda, then A is of the form lambda I. So it's this thing, actually, they call it a scalar matrix. It's just a scalar on the identity. Specifically, the eigenvalue is the scalar, right? Okay. So we know A is diagonalizable, right? So we know we have D equals P inverse AP. And we know that D would equal lambda ... however large this thing is, zeros here, zeros here. Since, I guess, A has only one eigenvalue, right? So that's kind of what we know, right? And we can see that, I guess we'll say, note, just quick, that D equals lambda I. That's going to be important, okay? So we have D equals P inverse AP, or lambda I equals P inverse AP, right? Or right there. And you might see where this is going. So we know P is invertible, right? So we want to show that A is lambda I, right? And so what you want to do is you kind of want to unpack this so you can get to A. So I'm going to take P of, on the left side for both. So then I would have P lambda I equals AP, or I could take and then this implies, we'll just say, so I can take P inverse on the right. This implies that P lambda I P inverse would equal A. And then here's the nice trick. Really, all these things commute, right? This is scalar, so you can pull it out. It's fine. Identity matrix, really I could even drop it because I have P inverse times it now, so I could just write P inverse, right? And so I don't even really need the I. And inverses are commutative, right? So everything here you can just swap around in any order you want. And the order we want is specifically the P's next to each other. So I'm going to take lambda I out in front. So lambda I times P inverse equals A, or what I want, right? Which is that lambda I equals A. And then, yay. Best way to finish a proof. And it's still out of box. But that's it. So it's just a lot of moving symbols around, right? Using some kind of commutativity here that pops up nicely. And then you get it. All right, so there's 2 of these kind of weird matrix properties out there, and there's this one called nilpotent, which we're going to do here, actually a problem with in a second. And then there's this thing called idempotent, I think is how you say it. Idempotent is the one that says A squared is equal to A, and nilpotent is the one where it says you raise a matrix to power and eventually it goes to 0. So for this one, again, I recommend you pause, try to solve it yourself, but I'm going to do it right now. So this one says that if A is diagonalizable, such that every eigenvalue of it is either 0 or 1, then A is one of these weird idempotent matrices where it's A squared equals A. All right. So same place to start as kind of all these problems. We have that some diagonal matrix is equal to P inverse AP, right? And I'm going to also add, and we know d squared would equal P inverse, well, sorry, actually, I'm going to do it the other way. And we know that when we have this kind of thing, right, we know A to the m is similar to D to the m. That's supposed to be an m. So we also have that, like, A squared is going to equal PD squared P inverse. I think I did that correct. All right. And that's going to be useful for us in a second. But first, note if the only eigenvalues are 0 and 1, then D squared would equal D. And that's just because, like, I'm going to erase this, but, you know, that's not too bad to see. If you have, let's just do a 3 by 3, say you have that, so big 0 here, big 0 here. If you square this kind of matrix, right, you're literally doing 1 squared, 0, 0 zeros. And then you're still going to get 1, 1, 0, 0 zeros. And, you know, they're the only two numbers in the world where, well, that's not true at all, -1. But these two numbers, for sure, you can square them and you just get back to itself, right? So D squared is equal to D, no matter how large D is, okay? Let me get rid of this. And so now I can kind of blend these two things, right? So then, so if I have this A squared, right? I know A squared is A times A, of course, right? And I know that A is equal to PDP inverse, PDP inverse, right? And, you know, these cancel off. I get PD squared P inverse, right? And then this is where I'm going to use my substitution, basically this. And so this equals P, that would D P inverse, right? Because D squared is D. And we know that PDP inverse equals A, right? Just by, like, the similarity up here. You can restructure this, and you know that PDP inverse is A. So that does it, right? So A is idempotent, since we've shown A squared is A. And that's it. All right, one more, just kind of showing you similar kind of thing, but for the nilpotent thing now. So again, pause the video, try it yourself. But I'm going to do it right now. So you have a nilpotent matrix, and that's just one where A to some power eventually is 0. It might take, you know, 14 million powers of A before it goes to 0, but it will happen. Okay, so it's just going to go to 0 at some point. And we know that A is diagonalizable, and we just want to show that A literally has to be the 0 matrix if this is happening. Okay? So for this one, I'm going to start off again. If A is similar to D, then we have that A to the m is similar to D to the m, where m is the first power that sends A to 0. Okay, so it is the power up here where all of a sudden it's going to be 0. Okay. So we have well, okay, yeah, I'll start with this. So we know that A to the m then by definition equals P D to the m P inverse, and this implies that D to the m equals 0. And that might not be super clear at first, okay, but we know that A to the m is 0, right? So I might even add that here. So 0, which equals A to the m, is going to equal P D to the m P inverse. And the reason is because P is an invertible matrix. So P can't equal the 0 matrix, right? You know, the determinant of it can't be 0, and the determinant of the 0 matrix is 0. 0 is just not invertible, okay? Oh, wait, I wrote equals. P is an invertible matrix, so P can't be 0. Likewise, right, then P inverse can't be 0. So the only thing up here in these three matrices that could be 0 is d to the power of m. So we're at that point, okay? But if you think about a diagonal matrix, just like note, d to the m equals 0 implies that d equals 0, right? And that's just like, you know, if you have, again, like some diagonal matrix and you're raising it to a power, and then what you get to do is whatever these entries are, right, you raise them, you raise them to the power, and the only way you're going to get the 0 matrix for whatever size it is out is if these things along here were 0. So we know that D has to be the 0 matrix. And then we basically have it, because now if we just go and kind of put all this together, therefore, if we go back to this part right here, A, which equals P dP inverse, now equals pop inverse, right? Which, most importantly, equals 0, right? You're multiplying a 0 in there, you're going to kill this thing off. And that does it. Since A equals the 0 matrix, we know, we are done. Okay, we'll just call it that. Beautifully worded proof right there. So a lot of these proofs I did today, if I was writing these up formally, I would definitely clean these up, but they at least give you the sketch of what is involved in proving these kind of things. There are lots and lots of problems in higher level math classes where you're using diagonalization and similarity and all that sort of stuff. Tons of proofs like this. If you want to go be a math major, you'll get very used to doing this sort of stuff. So that is it for this video.